Good day, class. Today we're going to pick back up in Unit 1, talking about a little bit more about domain and range, using the vertical line test, talking about intervals on which functions are increasing, decreasing, or constant. We'll discuss relative maximums and minimums. We'll talk about a new function called the step function. We'll also look at some piecewise functions, graphing them today, and we'll talk a little bit about even and odd functions as well. All right, so this is just the basic definition of a graph. Hopefully we're all very familiar with what a graph is. It's just a collection of ordered pairs, f of x, or x comma y, such that x is in the domain of f. Do remember that x, of course, is the distance from the y-axis, and that f of x, or y, is the distance from the x-axis. All right, so here's just a way of talking about domain and range when looking at a graph. All right, so it gives us a graph here, and it wants us to find a, the domain of f. All right, remember, domain is what x values does this graph touch. All right, we don't care how high or how low. All right, we just want to know from how far left to how far right. What do we include, not include? Is there anything in the middle that we have to take out? That kind of stuff. All right, so here we can see that the farthest left this graph goes is over here, is -1, and it is continuous all the way until over here. The furthest right this graph goes is 4. All right, so the domain of this function. All right, now we do include -1 because of that closed circle. All right, and then we do not include 4 because it is an open circle. So we have a parentheses there. All right, b, it wants to find the function values of f of -1 and f of 2. So we'll do that over here. F of -1, of course, we go to the x-coordinate of -1. We go to the graph at that x-coordinate, and we say, okay, what is my y-coordinate? Well, my y-coordinate is obviously right here at -5. So f of -1 equals -5. All right, and f of 2. So again, of course, we go to the x-coordinate, x value of 2. We go to our graph that is on that x-coordinate, and we say, what is my y value? Of course, that is 4. And then finally, part C says to find the range of the function. The range of the function are the y values that this thing covers. And when we write domain and range, we definitely want to write them in numerical order from lowest to highest. With the domain, that's pretty simple. We typically read things from left to right. However, with range, we actually want to go from the lowest point to the highest point. All right, so it's a little bit different than how we would normally think so, but please do not mess those up. Do not switch those around. All right, so the lowest point y value here is -5, and I will be including that because this is a closed circle. The highest point this graph goes to is +4. I will be including that as well because of this closed circle. So my range is from -5 to 4, including both. All right, here's just some explanations here. We don't really need all that. Okay, so the vertical line test, you should have seen this definitely in Algebra 2, quite possibly even in Algebra 1. All right, so basically the vertical line test tells us whether something is or is not a function. All right, so if you have a vertical line, and they give us random vertical lines here, but I'm going to make my own just so that I can kind of move it around here. All right, so if I have a vertical line, all right, well, I can move this thing around here. So and you want to be able to move it all the way around anywhere on the function. Right? Well, if this line ever touches the graph in more than one spot, then we say it is not a function. Obviously, this occurs all over the place on this graph, so we would say that a is not a function. All right, part B here, no matter where I move this line, doesn't matter where, right? It is always only going to be touching that graph in one spot, right? Therefore, graph B there is a function. Okay, so now we'll talk about increasing and decreasing. All right, so basically it's fairly straightforward. All right, a graph is decreasing if it is going down as we go from left to right. All right, it is constant if it stays flat as we go from left to right, and it is increasing if we are going up as we go from left to right. All right, now the important thing here, though, a lot of people, when they are asked where is this graph, decreasing or increasing or whatever, they typically will say from this point to this point. So like they'll give from x comma y to x comma y. That is incorrect. Okay, we only talk about from what x value to what x value. Okay, x values are typically used to describe where something is going on in a graph. The y values tell us what is going on. Okay, well, we know that the y values are going down because we know that the graph is decreasing or increasing or constant or whatever you're being asked about. We know what the y values are doing. The only thing that we care about is from what x value to what x value. All right, so for example here, we would say that this graph is decreasing, all right, from, remember I only care about the x values here, so from -2 to 0. Right? And you never have to worry about brackets or parentheses. When you're talking about increasing or decreasing, it's just always parentheses. Right? So you give an interval, from what x value to what x value. Right? This graph would be constant from 0 to 2. And this graph would be increasing from 2 to 4. All right, so do be very careful. Only from what x value to what x value. If you put the x and the y value from this point to this point, you will be wrong on a test or quiz. Okay, so definitely keep that in mind. All right, this is a really technical mathematical definition of increasing and decreasing. I don't recommend that you really look at this or even care about this. I think it's much more complicated to look at than just knowing something is increasing when it's going up, something is decreasing when it's coming down, and something is constant when it's staying the same as we go from left to right. All right, so determine the open intervals on which each function is increasing, decreasing, or constant. All right, so what I would recommend you do here is pause this video and then kind of, just write down real quick what you think where each of these graphs are increasing, decreasing, or constant, right? And then go ahead and hit play, and then you can kind of check yourself. All right, now, this first one typically tends to get people, right? It's obviously increasing here, and it's obviously increasing here. Right, but a lot of people actually mistakenly think that it's constant here. Okay, it's actually not constant. If you zoom in on the graph y equals x cubed, if you zoom in really closely, you can see that here it's always actually increasing, although it's increasing at a very low rate. It is still always increasing. So this graph is increasing, all right, from -infinity to infinity. All right. Well, if it's increasing everywhere, all right, then it's decreasing nowhere. All right. So this little symbol here, a lot of people mistakenly use this to represent the number 0. No. All right. This little 0 with the slash through it actually represents what is called the null set, right, which means that it is a set with nothing in it. All right, so it's basically, this is saying, excuse me, that it's not decreasing anywhere. All right, um, and we already talked about how this kind of looks like it's constant here, but it's actually not. So it's not constant anywhere. All right, this graph here, x cubed minus 3x. All right, well, also just as a side note, there's no arrows here, but we can kind of assume that it goes on forever and ever. If you kind of got really nitty gritty about it and just told me that the graph stopped right here and you said that it was increasing from like -1.5 to +1.5 instead of from -infinity to infinity, that's fine. I would give that to you. Now if there are obvious either arrows telling us that it does go on in both directions forever, then this would be the only option. But in a graph like this, I would kind of give you either. Additionally, if there's an obvious like closed or open circle at the end, okay, then you would have to end it, wherever those closed and open circles are. But again, if it's not obvious, if there's no arrow or closed or open circles, then I would be pretty lenient and accept either. All right, so here, this graph is actually going to be increasing in a couple of places, right? We're going up right here, right? So this graph is going to be increasing from -infinity to -1. Remember, we only care about the x coordinates, right? And this thing is also increasing from +1 to infinity. All right, this graph is decreasing from here to here, right? My graph is going down as I go from left to right. So from -1 to 1, again, these are always open intervals. We never have to worry about that. And this graph is constant nowhere, right? It's not flat anywhere at all. All right, here we have a piecewise function. This graph is increasing from here to 0. So I'll say -infinity to 0. Again, if you said from like -2 to 0 because there's no arrow or closed or open circles, I would give that to you. This graph is decreasing from 2 to infinity. Again, if you said 2 to 4, I would give that to you. And this graph is constant from 0 to 2. Remember, we only care about x coordinates. No need for anything involving the y coordinate whatsoever. All right, so again, here is a very technical mathematical definition of relative minimums and relative maximums. All right, again, I don't think that it's very beneficial for you with your kind of limited mathematical knowledge at this point to really worry about these very technical definitions. Really, a maximum, right, is kind of the top of a hill. All right, a minimum is the bottom, right, of a little valley. Right, I think of them as peaks and valleys. Right, if you think of these as kind of hills or mountains, the peaks are maximums, the valleys are minimums. It is important to note that when you're talking about relative minimums and maximums, for instance, if we had something like this, okay, this would be a maximum, this would be a minimum, those are easy, all right, but endpoints are neither. Like, even though I know you would want to say this is a maximum and you would want to say this is a minimum, because if you actually go back and look at this very technical definition, it says that it has to be the lowest point from both sides, right? So since you're not coming from this side or coming from this side, you can't actually call that a relative maximum or minimum. When you get into calculus, you'll do a lot more exploration with maximums and minimums and how to find them a much better way using calculus, a very exact way. And then you'll start getting into differentiating between relative maximums and minimums and absolute maximums and minimums. When you talk about absolute maximums and minimums, then you can actually include these endpoints. But we're not going to be getting into that in this course. So for the sake of this course, don't include those endpoints at all. All right, so it says, let's use a graphing utility to approximate the relative minimum of the function given by 3x squared minus 4x minus 2. Right, so we can go ahead and pull out our calculator here. We go to y equals, we say 3x squared, and I believe it was minus 4x minus 2. I'll double check that, yep. All right, and we can go ahead and look at the graph here. All right, so it's just a parabola, all right, and we know that the minimum will be the vertex here. So I can actually hit second trace. This is going to be a very important command, hitting second trace a lot for this course. All right, it allows us to find many things. All right, zeros, minimums, maximums, and intersections. We're going to use those 4 commands very often in this course. All right, so right now we're looking for a minimum. So you can either use your arrows and go down to the third option and hit enter, or you could just hit the number 3 and it will automatically do that. Right now, this graph is going to, the calculator is going to ask for a left bound. Right, basically, when the calculator asks for left bounds and right bounds, it's asking for like a little baby window of where you want the calculator to look. So for left bound, you just want your cursor to be anywhere to the left of the minimum that you are looking for. All right. Now you do also have to be careful if you're looking at a higher order polynomial and it has multiple maximums or minimums. You want your window, your left bound and right bound, to only be surrounding the minimum or maximum or 0 or whatever it is that you're looking for, only surrounding that one. Because if you have multiple of them, within a search window, it'll kind of confuse the calculator a little bit. So you can just go anywhere to the left of that minimum. You can hit enter. All right. The newer calculators give this nice line here. The older ones and the ones that we have in the classroom will just give this little arrow. All right, then it'll ask for the right bound. So you just go anywhere to the right. All right, so now you can see that the calculator is only going to be looking between these 2 arrows or these 2 lines. All right, so we can go ahead and then it'll ask for a guess. You don't really have to move the cursor like close. You can really just hit enter again and it will be fine. All right, so the minimum, it gives us an x and a y. Technically, the x just tells us where the minimum is occurring. All right, the y is the actual technical minimum. All right, but really, if you just give it as an ordered pair, all right, that is very sufficient. A lot of college professors will want you to say that the minimum is negative 3.33 at x equals whatever, because that tells us where. But for this course, if you just give us a point, I'll accept that. So this is 2/3 and negative 3 1/3. So 2/3 and negative 3 1/3 is 10/3. Please don't use mixed numbers. I hate mixed numbers. Improper fractions are much, much preferred. All right. And since it does say approximate, you could use decimals. That's fine. You could have said 0.667 and negative 3.333. Do please round to 3 decimal places, unless the situation dictates otherwise or unless you're told otherwise. All right, so now we're going to talk about the greatest integer function. All right, so the parent function of that is this. All right, this is not, an absolute value or anything like that. All right, this is actually its own function called the greatest integer function. All right, and it actually looks like a set of steps, which is why they call it the step function up here. Okay, but basically, whatever you plug into this, it spits back the greatest integer that is not greater than whatever you plugged in. Essentially, you're always rounding down. All right, now you do have to be kind of careful when you throw negatives in there, because rounding down actually is to the higher negative number, right? So if you were to do, f of x well, I'm sorry, f of, if we were trying to find f of negative 4.3, right? You're rounding down, but negative 4 wouldn't be rounding down because if you think of a number line, negative 4 is actually to the right of negative 4.3, so that would actually be rounding up. This would actually be negative 5. But with positive numbers, it's a lot easier. You're just always rounding down. All right, so now we're going to talk a little bit more about piecewise functions and graphing them. Okay, so last week we talked about evaluating these things. All right, well now we're actually going to graph them. Some other teachers may, specifically in Algebra 2, I know you do these. If another teacher taught you some other way that you are very fond of when it comes to graphing these things, that's perfectly fine with me. I don't care as long as it is correct. But the way that I'll show you is, will be the way that I think of it. And I think it's the fastest and most kind of expedient way to do it. But all right, so I'll just go ahead and put some axes on here. All right, so now I'll do this first piece in blue. All right, now what I think is the easiest way to do this, all right, is to kind of tell yourself where are you going to be breaking up the graph. And the graph is always going to be broken up wherever these conditions over here after the definition of the function, where the conditions kind of tell you. So since you're going to have one piece less than or equal to 1 and one piece greater than 1, x equals 1 is where this graph is going to be broken up. All right, so I like to just put a dotted line, and that just kind of tells me that that's when my graph is going to be broken. Okay. Now what I do is I take this number, whatever this number is, in this case 1, and I plug it into my function. All right, so if I plug 1 into here, 2 times 1 is 2, plus 3 is 5. So that tells me that I have the point 1, 5. All right, now because this is or equal to, it's going to be a closed dot. So 1, 5, closed dot here. Now, it says that this thing is true for all x's less than or equal to 1. All you have to do is pick any number you want less than 1. All right, well, 0 is less than 1. If I plug 0 in here, I'm going to get 3. So that gives me the point 0, 3. All right, so now I know that I only need 2 points for a line. All right, now you could keep going if you want. You could plug in -1, you could plug in -2, whatever you want. It doesn't really matter. All right, but once you have 2, that is sufficient. All right, now you'll want to use a ruler or something of that nature, I guess, for this. We'll go ahead and try to be a little bit more precise. All right, so there we go. All right. Now we can do the other piece. I will go ahead and do that in red. Right, again, I want to plug this number in. Right, I know that 1 doesn't go with both of these, but I still want to. So if I plug 1 into here, -1 plus 4 is 3. So that's the point 1, 3. Now this is just greater than, so it's going to be an open circle. So I have the point 1, 3, and I have an open circle. Again, this is valid for all x's greater than 1. I can pick any x I want greater than 1. So a nice easy one would be 2. If I plug 2 in here, -2 plus 4 is 2. So I would have the point 2, 2. Okay, now do be mindful. A lot of students like to put open circles all over the place. The only place you can have an open circle, all right, is on this dotted line. If you have an open circle anywhere else, you are wrong. All right, so do be very careful about that. All right, so again, I'll try to be a little bit more exact here. So I will start here. Okay. All right, and that is it. We are done. All right. We'll do another one here. All right, so again, I will go ahead and put some axes on here. All right, now what I would recommend you doing here, all right, again, I'll start with blue on this piece. What I would recommend you do here is pause this video, attempt to graph this on your own, and then go ahead and hit play so that you can kind of check yourself. All right. So again, I'm going to go ahead and put the dotted line where my graph is going to be broken up. That's going to be at -3. So there is my dotted line. Back to my blue. Right, again, I take this number and I plug it in. So -2 times -3 is 6, plus 1 is 7. So I have the point -3, 7. This is just less than, so it's going to be an open circle. So -3, 7, open circle. Again, this is valid for values less than -3. So pick numbers less than -3. -4 is a nice easy one. If I plug -4 in here, I'm going to get 8 plus 1, which is 9. So -4, 9. All right, so again, I can go ahead and put a line on here. All right, so there is the first piece of my graph. All right, I'll go ahead and do this section in red again. All right, again, I want to plug -3 in here. When I do that, -3 is 3, plus 4 is 7. So I have -3, 7, which is the same point. That's fine. It's still open though, because this is just greater than. All right, now this is valid for all x's greater than -3. You can pick any number you want. I'm just going to go ahead and pick 0 because it's really easy. So -0 plus 4 is 4. So I have 0, 4. Again, you can pick any number or numbers you want that are greater than -3, and it would work just fine. So I'm going to go ahead and get a line on here. Connect it there. And we're done. All right, so pretty straightforward, not too bad. All right. Exact same concept here. All right. Again, go ahead and pause this if you would like. I'm going to put some axes on here. All right, so. Oops. All right, I'll put my dotted line, which tells me where this thing is going to be broken up. That is going to be at -2. All right, again, I'll do my first piece in blue. Again, I just want to take this number and plug it in. So -2 plus 4 is 2. So I have the point -2, 2. Of course, it's an open circle because this is just less than. So -2, 2, open circle. And again, I can pick any value I want less than -2. I'll plug in -3, and I'll get -3, 1. 2 points is all we need for a line. So I will go ahead and do a line here. And we're done with that piece. I'll do the next piece in red again. Again, I can plug -2 into this piece now. -2 times -2 is 4, plus 3 is 7. So I have the point -2, 7. And it will be a closed circle because this is or equal to. And again, I can take any number I want greater than -2. I'm going to go ahead and just pick 0 again. It's an easy number to plug in. So 0 plus 3 is 3. So I have the point 0, 3. I can again, I only need 2 points for a line. So and we are done. All right, so we have another one here. Again, I'll go ahead and put on some axes. And again, I will put where my graph is going to be broken up. All of these are 2. You can have more than one spot where the graph breaks up, but in this case, in all the cases we've seen so far, we just have the 1. All right, so my first piece again, I will do in red. So if we go ahead and plug 2 into here, half of 2 is 1, minus 4 is negative 3. So we'll have the point 2, negative 3, and it will be an open circle because that is just less than. Again, I pick any number I want less than 2. Typically, I would just pick, 1 or 0 or whatever. But when you do have a fraction, be mindful that you're going to want to pick a, in this case, you want to pick an even number so that when you take half of it, you don't get something messy. But I'll just go ahead and pick 0 again. That's always a nice one to pick in, to plug in. When I do, I will get 0, negative 4. So I have the point 0, negative 4. Again, 2 points is enough for a line. So I will go ahead and do that there. We are done with that piece. All right, now my next piece, I'll go ahead and do here in purple. All right, now this just says when x is equal to 2, y is 5. That's just a point. Okay, it's not a straight line. A lot of people try to make that a horizontal line. If they gave us some range in which we had a constant number, then yes, it would be a horizontal line. But when it just gives us a single number, when x is 2, y is 5, that's just the point 2, 5. And that's it. There's nothing else to it. We're done with that piece. All right. I'll do blue down here for this last piece. Again, I take my number here, plug it in here. 3 times 2 is 6. So I have the point 2, 6. And it's an open circle because it is just greater than. But again, I can pick any number I want greater than 3. Plug it into here. I'll just pick 3. 3 times 3 is 9. So I'll have 3, 9, which would be up here. And again, we can do a line. And we're done. All right, so we have another one yet again. All right, now we notice here that one of these is not just a line, right? X squared minus 1, that will be part of a parabola. So whenever we have a point, we just need the 1 point. Whenever we have a line, any 2 points on that line can define that line, so we only need 2 points. But when it's something other than just a point or a line, you're going to have to get a few points until you can kind of easily determine the shape of the graph. So again, I'm just going to put some axes on here. And my graph is going to be broken up at 0, so right on my axis here. At the first piece, I will go ahead and do in blue. Right, so again, we can plug 0 in here. 0 squared is 0, minus 1 is negative 1. So that gives me the point 0, negative 1. It will be an open circle because this is just less than. All right, so now we want to start picking numbers less than 0. So negative 1 is less than 0. Negative 1 squared is 1. Minus 1 is 0. So negative 1, 0. Remember, this is a quadratic, not just a line, so we need, another point or two. If I plug -2 in here, -2 squared is 4, -1 is 3, so -2, 3. If you wanted, you could go again. You could do -3, and that would be 9 minus 1 is 8, so you would have -3, 8. All right, so now we can kind of see that it's just this piece of a parabola. Excuse my sloppiness on this little tablet pad I'm trying to use. All right, so then we can go to our next piece, point, of course, when we have x just equal to some number, and then it is equal to some number. Again, that is just a point. All right, so this will just be the point 0, -1. And because it's equal, of course, it's solid. So really, we're just filling in this open circle that was here since they kind of overlap. And then finally, I'll do this piece. Again, if I plug in 0 here, I get 5. So the point 0, 5, but it's going to be an open circle because this is just greater than. 0, 5, open circle. Again, this is true for anything greater than 0. So if I pick 1, I would get 7. 2 would be 9, so on and so forth. I know that this is just a line. And we're done. Right now we can go ahead and discuss even and odd functions. All right, so a graph has symmetry with respect to the y-axis. Whenever the point x comma y is on the graph, then so is the point -x comma y. A graph has symmetry with respect to the origin if whenever x comma y is on the graph, then so is the point -x comma -y. Right? A graph has symmetry with respect to the x-axis if whenever x comma y is on the graph, then so is the point x comma -y. Right? A function whose graph is symmetric to the y-axis is an even function. A function whose graph is symmetric with respect to the origin is an odd function. Okay, so these are very important pieces to note. Right? Do be mindful here that if a graph is symmetric about the x-axis, it's not a function because it would fail the vertical line test. All right, so we won't really talk about a whole lot of things that are symmetric about the x-axis because we primarily only talk about functions in this course, right? But things that are symmetric about the y-axis and the origin can be functions, so we'll talk about those a lot more. All right, so this are just some examples here. All right, this graph is symmetric about the y-axis, right? The y-axis right here. If you could kind of pick this graph up, if this were on a sheet of paper and you wanted to fold it along here, right, it would match up perfectly well. All right, this is an example of symmetry about the origin, right? For any point x comma y, we also have the point -x comma -y, right? And then this is symmetric about the x-axis, which I mentioned earlier. Anything symmetric about the x-axis is not even a function. So, right, a test for even and odd functions. This is an algebraic way that we can kind of see whether something is even or odd. We simply plug in -x for x, right? We find f of -x. If when I do that, it does not change the function at all, then we say that it is even. Right? If when we plug in -x, it gives us the exact opposite of the function, right? Then we say that it is odd. All right, so determine whether each function is even, odd, or neither. All right, so first I will look at g of -x. So I plug in -x anywhere where there's an x. So I say -x squared. I just plugged in a -x for this regular x. and then minus, and then I plug in a negative x for this x as well. All right? So when we do that, negative x quantity squared is still just x squared. And of course, minus negative x becomes plus x. Okay, so did this thing stay exactly the same? No, it did not, because this sign changed. Did it become, so it's not even, right? If it stays exactly the same, then we know it's even. Right? If it becomes the exact opposite, then we know it's odd. So is this the exact opposite? Well, no, it's not, because my x squared is the same, right? If this were negative x squared plus x, then it would be the exact opposite. So since it's not the exact same, and since it's not the exact opposite, right, then we say that this is neither. All right, now I will look at h. So I will do h of negative x. All right, so now I'm still plugging in negative x wherever there's an x. So I have negative x squared plus 1. All right, well, we just talked about negative x quantity squared. Negative x times negative x is positive x squared plus 1. All right, well, did this thing stay exactly the same? It absolutely did. All right, so since these things are exactly the same, it didn't change at all, then we say that this is even. And last but not least, we will look at f, and I will look at f of negative x. All right, so when we do this, we have negative x quantity cubed minus 1. All right, well, negative x cubed is negative x times negative x times negative x. So that's actually going to, the negative is going to stay, negative x cubed, and then we still have minus 1. So is this the exact same as what we started with? No, it is not. So it's not even. Is it the exact opposite of what we started with? No, it is not, because this is still a negative here. So it's not even, it's not odd. Therefore, this is neither. All right, an example of being exactly opposite. I can come up with one of those for you since we didn't see it. Let's just call this j of x. And maybe I have x to the 5th minus x. All right, so now if I look at j of negative x, all right, this becomes negative x to the 5th power minus negative x. All right, so when we do this, now just to make it easy on yourself when you're doing higher powers, whenever you take negative x raised to an even power, the negative just goes away. Right? So like negative x quantity squared is just x squared. Negative x to the quantity to the 4th power would just be x to the 4th. Negative x to the 6th power would be positive x to the 6th. Right? But however, when it's odd, like negative x to the 3rd power, the negative comes through. And that happens with any odd. So this will actually be negative x to the 5th. And then minus a negative x becomes positive x. So is this thing the exact same as what we started with? No, it is not. So it is not an even function. Is it the exact opposite of what we started with? Yes, it is, right? This term is opposite and this term is opposite. So it's the exact opposite. So we would say that this is an odd function. And we'll skip that. Of course, your homework will just be on Delta Math. So that is it for today. Look for your assignment on Delta Math and have a good day.